Okay, this video is about U-substitutions, an alternative approach, and it's a bit more of a theoretical approach to U-substitutions about why they work and maybe some of the little odd questions you had about why certain markings appear in the process of doing a U-substitution. And in order to fully explain this, we're going to go all the way back to derivatives. So you remember from derivatives that if f is a function of x, then the derivative of f can be written as either f prime of x, which is what most videos on the internet and most textbooks use as well. You can write it as capital D subscript x f, which is a little bit of an unusual notation, but the textbook that I pull a lot of the homework from, that is the Swakowski textbook, uses this. Or you can write it as df dx. Now, this third form here, this sort of fractional form, df over dx, that is the most detailed form, because you can think of a derivative as the slope of the tangent, and that's going to be the limit as delta x approaches 0 of delta y over delta x, and when these deltas get really small, remember delta means change in y over change in x. When the change gets really small, it becomes a derivative, but it retains its fractional nature. So you really can think of dy over dx or df over dx as the derivative. And before a bunch of math majors watch this video and jump on me or get on my case, I will admit that this works really well as long as you're only doing calculus of one variable, or its sort of flip side, which is differential equations of one variable. Works pretty well there. Once you get up to multivariable calculus, or its sort of reciprocal operation, which is partial derivatives, or partial differential equations, then this does start to break down. But even up to some very elementary partial differential equations, this approach works. So just to remind you what I mean by delta y over delta x, if you have a function that looks like this and you have one point of interest, call it with coordinates x, y. One second, let me go get a couple more office supplies here. Okay, so if you have a point right here, which is going to be x plus delta x, and then we'll follow that upwards till it hits the function, and then over until it hits the y-axis. Okay, it didn't quite work there. All right, close enough. So that's y plus delta y. And this distance here is change in y, or delta y. This distance here is change in x, or delta x. And we draw I think it's called a secant line between these 2 points. We end up with this, which is not the same thing as a derivative, but as the delta y gets smaller and smaller, if we're going off of that point there, we get this second, slightly steeper secant line, and as those 2 points that make up the secant line get smaller and smaller, in other words, as your delta x approaches 0, then you eventually end up with a tangent line, which is this steep and relatively long third line that I drew. So, slope of the tangent, in other words, that slope of the tangent is going to be the same thing as the derivative. Alright, so this notation, whether you write dy dx or df dx, this notation allows us to approach U-substitutions in a slightly different way. And I say slightly different because practically there's not a whole lot of difference, but it does give you, maybe answer some slightly nagging questions. And that's first, identify U. And that's going to be the same as we've always done. Take basically the innermost function in a compound function. Take du dx and use algebra to get dx equals whatever. In other words, isolate dx out of the algebraic statement you get when you say du dx equals stuff. Then you substitute both the u you got in step 1 and the dx that you got in step 2 back into the integral. Then you should get an integral that conforms to one of our integral identities, or something really close to it, something where we can use the properties, and then followed by the identities to solve it. Alright, so this is one of those things that is much easier to illustrate through example than it is to illustrate through text. So let's get into some examples. Okay, example number 1. Let's say we have this x squared, integral of x squared e to the 3x cubed dx. This marking right here, that's a third power. Alright, so like I've said before, you want to identify u as the innermost function. So x squared times another function, that doesn't look like that's more of an outer function. We have the 3x cubed, that's the function inside of the exponential function. So let's start with that as our u. Then we take the derivative of u with respect to x. In other words, we take du dx. And this is a simple power rule application, so the 3 comes down, so we start with the 3 that started out front, and then we're going to multiply that by 3x squared. Now, there should be parentheses, not square brackets. Do a little bit of simplification, and you end up with this, du dx equals 9x squared. Now, here's the part that's slightly different from anything else that I've been able to find relatively easily on the internet. If you multiply both sides of this by dx, then the dx's are going to cancel out on this side. And then you need one more step. Remember, our goal is to isolate dx. And that's going to be to divide both sides by 9x squared. Okay, so on the du side, we end up with this. Okay. Now, here's where things get a little unusual. What we're going to do is we're going to substitute both this equation back into the integral, and we're going to substitute this equation back into the integral. And we're not going to mess with this x squared that's not part of the u yet. We know that that's going to be u, but let me show you how this can sometimes be a little bit more, I don't know what the right word is, methodical than some of the other approaches. Okay, so leave the x squared alone. And then we get e to the, 3x cubed, that's the same thing as u. And we take out the dx, and we put in the 1 over 9x squared du. Okay, hopefully you see where this is going. The x squared here cancels out with the x squared down here, and what we're left with is integral of 1 over 9 e to the u du. Alright, well this is relatively easy. Take the 1/9, move it outside. And integral of e to the u du is just e to the u. Don't forget the plus c. And last but not least, don't forget to back substitute the original function of u back into here. And so we get 1/9 times e to the 3x cubed plus c. All right. So that's the idea behind this new approach. And it has two distinct advantages. First of all, with the older approach, you had to define u and then take the derivative of u, and then for some reason that you really didn't understand, you put a dx at the end of it. This process explains where you get that dx from. If you really want to understand what du is, you really start with du dx and then multiply both sides by dx. So that's one nagging mystery where the dx comes from. One way to think about it is it comes from this process. The other thing that it might make a little clearer is sometimes you got to do a little bit of algebra over here. Like if I wanted to do this the old-fashioned way, then I would have to multiply this by 9 and then divide it by 9 at the same time. And you don't have to do any of that clever algebra here. You just isolate dx and then throw this whole shebang back into the integral, and then the algebra or the fairly elementary algebra becomes much more self-evident. Okay, so we're 12 minutes into this video. I'm going to show you 2 more examples of this in the next video.